All right, welcome back. So far we have been talking about just the direct current circuits. Now, from today, we'll be focusing on alternating current circuits. So, we learned previously, typically, electric generator looks something like this, a coil in the magnetic field, and then it's rotating. So the angle, the coil's plane and the magnetic field makes it as a function of omega times t, omega being the angular frequency. So then as a result, induced EMF is a sine function. So typically, as for electric generator, it supplies you as an alternating current because half of the time the signal is positive in voltage, and then the other half of the time is in the negative territory. And in reality, electric generator looks much bigger. For hydro electric generator, use the potential energy, gravitational potential energy of on water in the dam, and then generate the turbines there. So then the coil is generated, and then in the circuit, the magnetic field there. So this is the size of that. It's pretty huge. So the person is somewhere like that, halfway. It looks like of the space only. Okay. And then the electricity will be delivered through power lines, high voltages, and then um, they will be then transmitted to the sent it to the household for usage. Okay, so for an AC signal, it's really it's changing back and forth, back and forth. So the voltage and the current as well. On the other hand, the DC current, directed current, is just a constant values. Okay, so alternating AC is a voltage could be a sine a sine function, sine omega t, where omega is the angular frequency that is related to the frequency f multiplied by 2 pi, and the current might also be just a sine function or cosine function, but they are pretty much the same. Sine and cosine is just with a shift of horizontally to each other. Okay. In some textbook, you might be seeing people writing the voltage as a cosine function, and then also current as a sine cosine function. If you have a resistor in the AC circuit and the voltage is a sine function, the current through it will be also a sine function. Okay, so this voltage as a sine function is V naught sine. V naught is the maximum at any given time. All right. So for a simple AC circuit, you will just have a resistor on the circuit. So then the current and the voltage are both a sine function because according to Ohm's law, voltage is equal to I times R, so I equal to V over R. Then Fv is a sine function with a maximum value or peak value, then the current will also have a peak value, which is the peak voltage divided by the resistance and the same sine function. So when the current or voltage peaks, the current also peaks. Okay, so they are in phase. So in the scenario that the current and the voltage, they peaks at the same time and then they minimize at the same time, we call them in phase. Otherwise, we call them out of phase. Okay. So if you have an AC signal, then current and voltage are both sine or cosine function. So then the average of them will be both zero. So it doesn't make a lot of sense when calculating the electric consumption using the average numbers. Okay. Instead, the root mean square quantity, root mean square voltage and current is used to describe the average power, as we'll see later. But the root mean square quantity is defined as the quantity scored, and then you take average of that. That will be equal to 1/2 the maximum score, and then you take square root of the left-hand side equation that becomes the root mean square quantity of it. So it's just the square root of the average score of the score average, okay? Of the quantity squared and to be averaged in that sense. Because when you average the quantity, now it no longer becomes a sine function, which is half the time is positive, half the other half is negative, but it now will just be positive all the time, or zero. So then the average of this quantity score will be just 1/2 of that. Okay. So to calculate the root mean score, you square root of the quantity score and then take the average. Okay, or you can do the 1/2 of the maximum value score and then take square root of it. So the root mean score of the quantity is equal to 1 over square root of the maximum. So then when you're calculating the average power consumed by the resistor in the circuit, you can use I squared times R, which I is a sine function. So then that has to be squared. So then it gives you the peak value in current square times R times sine of omega t squared. So for the average power, then you average that expression here. So I square is a constant number, peak value R is a constant number. So then the average will be just on this sine square omega, okay? So this guy squared will be equal to 1/2 of the maximum, okay? So then maximum of sine is 1. So then this average of this sine square will be just 1/2, okay? So 1/2 I squared peak. And 1/2 of the peak value square is equal to the root mean square squared, okay? So then it's equal to I root mean square squared times R. So P average then is still equal to I squared times R, but instead of using R, you just using I, you use root mean square of I, okay? You can also calculate the average power by using V square over R. Similarly, V is a sine function, so V peak square and then sine omega t squared, and then over R. And to take average of this whole expression, which is the average power, the V score and R, they are constant, so they come out. So the average of the expression is really averaging on this guy and then multiply the constants. Again, sine of the score average will be equal to 1/2, so that becomes 1/2. But 1/2 V score peak is equal to then the V root mean squared. Okay, so P average is now V square RMS over R, or V RMS square over R. You can also use V RMS times IRMS just similarly. So you can do the same way of V peak sine omega t and then times I peak sine omega t. Okay, in that sense, similarly, you can prove that it's equal to VRMS times IRMS. Okay, so either way, but P average is going to be equal to VRMS IRMS or equal to this guy, V square RMS over R, or I square RMS over R. Okay, so again, those similar terms. Now, for your appliance, the specification list are in RMS value. So for example, the power, that's the average power. So it's calculated by the RMS of the voltage and current. And then voltage given is the RMS quantity, and the current given is the RMS quantity. Okay, so the 120 volts household AC, that is the RMS value of the voltage. So the maximum could be higher. It's around 170. Basically, this guy multiplied by square root of 2. All right. So this first example of the day. So in many countries other than United States, so across the globe, there are different voltage used. So here we use 120, but in European countries, most of them use 240. And somewhere else, people will be using 220 or 110. So anything between 100 to 240 could be possible, okay, as you travel abroad. All right. Not only the voltages are different, so you might want to take an adapter as well, because the plugs are also different. Okay, so if you would have to travel to abroad, country abroad, and then so think about, in addition to the voltage changes, check your electronics chargers to see the specifications if it can adapt to 100 to 240 volts. In addition, the plugs. Okay, you might want to take an adapter plug to go along with you. But take a look on this one. It says the European wall socket has 240 volts. What will be the maximum? Okay, so so the maximum value, you are given the RMS quantity as a specification. So the maximum then will be just because according to the RMS quantity of voltage, that is equal to 1 over square root of the maximum. So the maximum will be equal to the square root 2 times R VMS. Okay, so square root 2 times 240 volts. That gives you 239 volts on this one. Okay. All right, let's go back to the slide. So we have just looked at the resistors in the AC circuit. So it's pretty simple. Now let's look at the inductor, and then later on we'll be looking at the capacitor. Okay, so in an AC circuit, the current and the um, voltage on the inductor, they do not actually peak at the same time. Okay, so think about if you have an inductor now as the switch is first closed, right? So we know for the inductor, once the switch is closed, it's kind of charging it. So the current, it goes up from 0 to a certain value. Okay, so it goes up like that. Just like you charging the capacitor, the voltage goes up like that. In this case, the current goes up in the inductor like that. So your voltage could peak at initially, but your current will start from 0. So that means your voltage actually peaks first, and your current will follow later. So, and also you can also derive this by using integration. So as your voltage is a sine function, then because voltage on the inductor is equal to L di over dt, okay, so then you can move dt to the other side equation, L also to be the other side. So integration on the right hand side of di will give you current as a function of time t, and the integration of this side. So this is sine function that gives you a cosine function, okay? So sine and cosine, they do not peak at the same location. So there's a shift of 90 degrees, okay? So when you plot it, the voltage, if it's a sine function, in this case, it's going to be a minus cosine function. Then the current is a sine function, okay? So it doesn't matter, but there's a shift of 90 degrees. So, or actually, this is the voltage. The yellow is the voltage, and the current is the green. So the current is lagging by 90 degree or pi over 2. So the voltage leads by 90 pi over 2 or 90 degrees. Okay, so if you have voltage as a sine function, and then the current will be a cosine function or minus cosine function in that sense. All right, so there's similar reactions of the inductor to the signal, AC signal applied, just similar to the resistor react to the signal. Okay, so but not exactly, because the current and the voltage, they do not peak at the same time. But in this case, they are kind of having a phase shift. So this kind of reaction, we call it as reactance of the inductors, and it's called inductive reactance for the inductor. So we use symbol X instead of R. So X for reactance, and then sub L for the inductor, so inductive reactance. And later on, we'll learn X sub C, which is the capacitive inductive reactance. Okay, so that is reactance for the capacitor to the AC signal. So this is equal to, so according to what we get out of the integration, we get I current is equal to peak value over omega L. Okay, so over here, omega comes out here. So in this case, so then XL is equal to omega L, or you can write omega as 2 pi times F, because that's the angular frequency. Okay, so if you are just given frequency, remember, multiply the F by 2 pi to the to become the omega. Okay, for omega. All right, so inductive reactance is equal to omega times L, and that has the same units as resistance in ohms. XL is equal to omega L, and then omega is equal to 2 pi F. Okay, so you can see as the frequency increases, the inductance reactance for inductor also increases. Okay, so proportional to frequency. Let's take a look on this one. So it says that you have inductor has the reactance of 100 ohms at 80 hertz. So you are given then inductive reactance XL equal to 100 ohms. Okay, and then it says frequency. So that's F, not angular frequency. Okay, HC. What's the inductance? So L equal to 1. Okay, so XL equal to omega L and omega equal to 2 pi F. So we can write actually XL as 2 pi F times L. So then L equal to XL over 2 pi F. Okay, so remember there's a 2 pi multiplied by the frequency. So 100 ohms divided by 2 pi times 80 hertz. That gives you 0.199 Henry for the inductance. Okay. And B says if your frequency becomes twice the original one, then what will be your XL? So if it doubles, right? So then this guy doubles, so this will double. So simply like that. So we don't necessarily have to calculate it. Okay, so just analyze the equation and then we'll see that right away. Okay. All right, let's go back to the slide. So now let's take a look on the power consumed on the inductor. So let's use the V times I. So V as a sine function and then I because it's shifted at 90 degrees, so it's effectively a cosine function. Okay, so then V peak, I peak will come out because those are constants. We can put them together. Sine and cosine, we can put them together. Now sine times cosine. So remember one of the trigonometry identities, sine theta times cosine theta is 1/2 of sine 2 theta. Okay, so then it becomes 1/2 of sine 2 theta. Theta being omega times t. Or if you remember, sine of 2 theta is twice of sine theta times cosine theta, the other way around. So then P equal to 1/2 V peak, I peak, those are constants times sine of sine function. So then the average will be on the power will be average on this expression, but not on those constant on this function, sine function. Okay, so average of sine, because sine goes from positive, negative, right? So average of sine function will be 0. So then essentially the average power on the inductor will be 0. So that means the inductor doesn't consume any power, right? Because the power average is equal to 0. Okay, so an inductor in an AC signal or AC circuit does not consume any power then. Okay, now let's turn to a capacitor in the AC circuit. Okay, so for a capacitor, when you charge it, remember when you have the switch on an RC circuit, right? So the voltage start to build up, right? But the current goes down. Okay, so if your voltage, so it's a sine function like this guy. Now the current according to dq over dt, and then q on the capacitor is C times V, right? So C times V, and then derivative of that guy. So you'll see that derivative of sine becomes a cosine, right? So but then omega comes before that. There's a C comes in there. So then omega C, and then cosine. Okay. Cosine is actually a sine of omega t plus pi over 2. Okay, so from this equation, you'll see actually when t equal to 0, this guy is 0, but this guy is maximum. The I is maximum. Okay, so in this case, the other way around, the current peaks first, and then the voltage peaks later. Okay, so by pi over 2 in radians or 90 degrees. So the current is leading, and then the voltage follows. Okay, for a capacitor in the AC circuit. So if we look at the expression for the current for the capacitor, this is omega CV, okay, cosine. So you can write this as, again, voltage divided by something, but rearrange the term, it becomes 1 over omega C. So this is called the reactance for the capacitor or capacitive reactance. So as X sub C, in this case is 1 over omega C. In the previous case for inductor is omega times L, right? So one is omega times L, the other one is 1 over omega C, okay? So in this case, you can see if the frequency increases, the reactance decreases, okay? So then it's the inverse proportional to the frequency. Capacitive reactance Xc is 1 over omega C. Again, omega is 2 pi times F. The SI unit here is ohms, okay? Just like the resistance again. And if we look at the power consumed by a capacitor in an AC circuit, then again, we do V times I V is sine function, I will be a cosine function actively because now it's leading by 90 degree again, okay? So VI peak, sine, cosine together. Okay, sine and cosine becomes 1/2 of sine twice of the angle, okay? So the average again will be on just on this guy, the sine function that will be again goes to zero, okay? So then a capacitor does not also consume any power in an AC circuit either. So we know capacitor stores energy, right? So it only stores energy, just like an inductor. So both cases they store energy. One in terms of electric field, the other one in terms of the magnetic field. Magnetic field for inductor, electric field for capacitor. Okay. All right, let's take a look on this example here. So it says calculate or predict a 22.0 microfarad capacitor is connected to an AC generator with an RMS voltage of 118 volt and frequency of 60 Hertz. What's the RMS current in the circuit? If you wish to increase the RMS current, what you add? Should you add a secondary capacitor in series or in parallel? Find the value of capacitance that should be added to to increase the RMS current to 1.50 amps. Okay, so let's start with writing out the norms. So we are given a capacitor of 22 microfarad, that is 22 10 to the minus 6 farad. And we are given a VRMS is 118 volts. We are given the frequency F is 60 Hertz. Okay. So this guy is in RC circuits, or just the circuit, the AC circuit. Okay, so you got something like that. Okay, this is a 22 micro, 118 volts and 60 Hertz. What is the current? All right, so the current I is equal to V RMS over XC. Okay. So if you go a couple slides back, so if we are doing RMS current, it's VRMS over that because peak current is equal to V peak over XC. Or a few more slides back, you'll see that actually I is equal to just I equals to V peak, okay, over the XC in that sense, sine omega t plus pi over 2. Okay, so anyway, so then for peak, you take peak. Okay, for RMS, you take RMS. Okay, so according to that. But in this case, it's asking for RMS, so we do that. Okay, so you calculate XC first, and then you just divide it by the VRMS. Okay, so XC will be 1 over omega times C. All right. So then IRMS is equal to omega C. So this over that, right? This is inverse of that in the denominator, so it flip up. Okay, so VRMS. Okay, so omega is 2 pi F, so 2 pi times 60 Hertz. That's omega times 22 10 to the minus 6 farad times 118 volts. Okay, so that gives you 0.97 0.9 amps, about 0.98 amps. Okay. So B, it asks you if you wanna increase the RMS current, should you add a second capacitor in series or parallel? So you can add a second one in series with this guy or parallel, right? But to increase the current, so that means you want so the current is like that, right? So you want this equivalent C to be increased, all right? So in order to increase, so we can call this as C1, okay? So C1 is 22 microfarad, and then C2, that's what we are looking for later on in part C. But if you want to increase, you'll actually add them up, okay? So when you add the two together for the equivalent, then you put them in parallel, okay? So you're going to put them in parallel, because when you put them in series, then you do one inverse of that guy, and then inverse to be CEQ. So CEQ will turn out to be smaller than either of those two if you do that, okay? So they should be in parallel instead of in series, okay? So the answer will be in parallel for that. And let's see, find the value of that second one. Okay, so we could find the CEQ first by using the new RMS, and then just minus C1, right, for C2. So in that sense, so I RMS prime is equal to omega C EQ, and then VRMS. Okay, so CEQ equal to then IRMS prime over omega VRMS. Okay, so that will be the new current 1.5 over, again, 2 pi times 60 for the omega and 118 volts. So that gives you 33.72 microfarad. Okay, so 10 to the minus 6 on that guy. So C2 then added will be CEQ minus C1, which is 33.72 microfarad minus 22.0 microfarad, which is 11.7 microfarad or 11.72. Okay, but keep 36 fixed only for 11.7. All right. Now let's go back to the slide. So when you have inductor or capacitors, or maybe both, and in addition to the resistor in the circuit, so really the current and the voltage, they do not peak at the same time. Okay, so that means there's a phase difference between the two, the voltage and the current. Okay, so in order to visualize the phase relationship between current and voltage in the AC circuit, we use phasor. The definition of phasor, a phasor is actually a rotating vector that has magnitude and direction, because a vector has magnitude and direction. Okay, and this rotating vector has length of maximum voltage. If we are talking about voltage, we call it current or the voltage phasor, or it has a maximum current if we are referring to a current phasor. Okay, so it's rotating around with the origin, and then with the angular speed of the angular frequency omega. Okay, so omega is equal to 2 pi times f. Okay, so at any time instance, then the current or the voltage is then the vertical projection of this phasor. Okay, so if you are looking at the current, then I current will be equal to this max value, and then its projection on that. Okay, so sine of that guy, and then voltage will be sine of that guy too. All right. So for phasor, the phasors for a capacitor in the circuit, so the current actually is leading the voltage. So in that sense, the current phasor will be in the green here. And if we start with the current as the omega t, So then current at any given moment will be I max sine of omega t, right? And then the voltage then will be equal to this guy, which is the V max times sine of omega t minus pi over 2 because it's lagging by 90 degrees or pi over 2, okay? So then it's at any given time for the voltage is the y projection of this vector, okay? So this vector will be then leading by 90 degree of the voltage phasor. So for an RC circuit then, okay, so the current and voltage on the resistor will be in phase, but on this two will be not in phase. So we can visualize them on the phasor diagram. So I max, okay, so that's the current phasor. I max times R, that gives you V max, okay, so that's the voltage phasor on the resistor. So these two are on the resistor, okay? Now the current, because those two are put in parallel or in series with each other. So the current on this one and this one will be the same, okay? So, so then this will be the current phasor on the capacitor, and the voltage phasor will be lagging by 90 degrees. So then it's this guy, okay? So, but it's times I times the reactance of the capacitor XC. Okay, so you have this guy and that guy. So the two voltage phasor on the resistor and then on the capacitor should add up to be the voltage of the whole circuit, right? So these two will add up, but those two are vectors. So you cannot just add them up numerically, but you have to do them in the vector addition. So these two happen to be having an angle of 90 degrees. So then this is the diagonal line of this rectangular shape. Okay, so it will be this square plus that square. So the maximum voltage on the whole circuit will be equal to square root of the maximum on the resistor plus the maximum on the capacitor. Okay, so I max R square plus I max XC square. Okay, the I max a common factor, you can factor it out. So then it's I max of square root of R square plus XC square equal to the V max. So in the under square root, you have those two added together, R square plus XC square. Okay, so we call them the sum of those to be just the impedance. So then we can apply Ohm's law there. V equal to I times R. In this case, replace R with Z. So then V equal to I times Z. Okay, where Z is the called impedance of the circuit. Okay, so for the RC circuit, you have R square plus XC square. Okay, equals to XC is 1 over omega C. Okay, so to that to be squared. So impedance also has the SI unit of ohms because the resistance is in ohms, reactance is also in ohms. Okay, so then there's an angle between the max to the current here. Okay, the max voltage phasor and the current phasor. So that angle is called phi angle. So cosine of phi you can see is equal to adjacent to divided by hypotenuse because this is a right angle triangle. Okay, so I max R over I max Z, so that is equal to R over Z. And if you look at the power in the circuits, okay, so it's I square times R using root mean square quantities, okay. So I, you can write one of them as V RMS over Z. So then the whole thing will be V RMS I RMS times R over Z, okay. So R over Z happens to be the cosine phi. So this is then also called the power factor, okay. So power factor will be R over Z of the circuit. Okay, so let's take a look on this example here. So it says determine the power factor of an RC circuit with R equal to 4, C equal to that. And then connect to the RMS of 24 voltage and then frequency of 150. Will the power factor of this circuit decrease or increase or stay the same if the frequency is increased? Okay, so let's take a look on this. So the power factor is equal to cosine of phi, which is equal to R over Z, right? So what we learned earlier. So cosine of phi is the power factor equal to R over Z. So it gives us R. We just need to find Z. Okay, so Z is equal to square root of R squared plus XC squared. So we can calculate Z first. This is square root of 4.3 ohms, kilo ohms. Okay, so times 10 to the third. So let's just use everything in SI units so then I don't have to write units. Okay, so 1 over omega C, omega is 2 pi times 150 hertz, and then times the C 0.35 10 to the minus 6. Okay, so everything to be squared. So this gives you 5.02 times 10 to the third ohms in ohms. So then we can calculate cosine phi is equal to 4.0 times 10 to the third, right? Divided by 5.0, pretty much 10 to the third. So that gives you 0.8 as the power factor on this one. Okay. On B here, power factor is equal to R over Z, which is R over square root of R squared plus, right? 1 over 2 pi F C to be squared. So it's asking you now if your frequency increase. So this guy increased, right? So this thing will decrease. The whole thing down here will decrease. So then that will be increase. So the answer will be increase, right? So increase on the whole thing. Okay, so the power factor will increase as your frequency increases. All right, I think we'll just stop here for today, and then we'll come back another time for the remainder of the chapter. Okay, see you guys later. Bye.